Welcome back to another VESPA tutorial. In this tutorial, we'll be taking a look at the Spectral Processing tab in the Analysis subprogram of VESPA. In case you haven't watched them, please go back and watch the VESPA installation video as well as the Analysis overview video. We're also going to make use of the tutorial data, so in case you don't have that, you can download it from the VESPA wiki, and you can find the links in the description of the video below. So I'm going to go to File, Open, Desktop. Here's where I store my tutorial data. Tutorial 6, and select Press CP0 and Open. This will bring up the data we'll be working with today. This is just a single voxel experiment from a press with a 26 millisecond echo time. Down here below you see the three tabs called Raw, Spectral, and Fitting, which we've discussed in the overview video. Today we'll be focusing on the Spectral tab. Let me walk you through the different options in the Spectral Processing tab. First of all, I would like to slightly change the appearance of the data. I'm going to go to View, Zero Line, and select Show. So this turns on the zero line going through the data. I'm also going to go to X-axis and select Show, and currently it's set to ppm. And once I select Show, the X-axis and ppm appears here. I'm also going to make sure that my data type is real, and it actually is real, which is good. And I'm going to go back to zero line and select, instead of middle, bottom. So this puts my data here at the bottom, where I can, I guess, easily use the maximal amount of space in my plot. So before we delve into the different options, you should understand the basic function of the Spectral tab. And the entire function of this tab is to help you sort of pre-process the data before fitting. The better your data is, the higher the quality, the easier and more reliable the fitting becomes. So if you have poorly phased data or data with large water components or eddy currents, all of which can be corrected through this interface, you probably are better off fixing it on the Spectral tab to the best of your ability before going forward with the fitting process. So let's quickly go over the different options. So there's an option here called Plot B in case you have an additional data set loaded. And here you see on the top, we only have one data set loaded. We can load a different data set by going to Open and selecting a different data set. In this case, I'm going to just reselect the same data set. So now you see I have the same exact data set, but now it's open on a different tab. So I can switch between the different tabs. And now, going to the original data set, I can select to plot the second data set below it. So on the top plot I have the dataset 3. On the second plot I have dataset 4, this one, and the bottom plot shows the difference between them. This can be very useful for comparing plots, and you can also choose what to see exactly. So you can choose in the third plot to plot the first minus the second minus the first, or sometimes the sum of them. This is useful, for example, if your second spectrum for some reason is, say, flipped, maybe because you're doing some sort of spectral editing experiment. So then the sum would actually give you the residual, not the difference. So I'm going to turn this off because I'm not interested in comparing anything at the moment. The next line lets you manipulate the FID and the Fourier transform, the spectrum. Chop lets you switch between the two halves of your spectral space. FFT lets you turn off and on the time domain Fourier transform. So if it's on, you see a spectrum. If it's off, you'll see your FID, free induction decay. By using the central mouse button, I can zoom out vertically. And it's interesting, by the way, to note, if we zoom in by holding the left mouse button and dragging, that this FID looks like it's very fastly modulated in time. If I turn off chop, suddenly the FID looks a lot more sensible. And the reason for this is that, going back to the spectral domain, remember that chop switches the two halves of the spectral space, and this corresponds in the time domain by, if you're familiar with Fourier theory, to a multiplication of the FID by a function that varies very quickly between +1 and -1. So in effect, this is exactly what you see here. By turning off chop, you're actually turning off this modulation. You can also flip the x-axis between left and right. Perhaps if your data is flipped, this makes sense to flip it accordingly. There's an option here for eddy current correction, and there are a couple of different options, different filters, each of which is based on a different paper. We're going to go into eddy current correction in a little more detail in its own specialized tutorial, so I'm going to leave it as it is for the moment. The second option after eddy current correction is signal filtering, and this is usually applied to water. And there are two water filters here, a finite impulse response filter and a Hamming filter, and also a singular value decomposition filter. And this is my personal favorite, simply because it works so well. And once again, this deserves a video of its own, so I'm going to keep it for a subsequent video. So you should just know that it's there, and it's usually used for filtering out unwanted water signal. Zero fill multiplier lets you add zero filling to your free induction decay, and as a result, interpolate your spectrum. So we can go to the free induction decay by turning off the FFT, and by selecting a zero fill multiplier of 4, you can see that I've added 4 times as many zeros as I had in points in my original FID. So the more zeros, the more interpolated your spectrum becomes. After, say, a zero filling of 1, you don't really end up getting any worthwhile new information, and just make the spectrum maybe look a little smoother, but it just adds computational complexity without adding information. I'm going to go back to the spectrum. Another interesting option here, after zero filling, is apodization. Apodization lets you apply a filter in the time domain, which basically lets you trade line width for signal to noise. So the higher the width of the apodization filter, the less noise you have, but also the lines become broader. I'm going to reduce the width here. You see that the narrower the width, the more noise we get, and the narrower the lines. So this makes sense if you have very noisy spectra and your lines are maybe slightly narrow, so you can stand to have some apodization. There are different apodization filters, and you can experiment. There's a Lorentzian one here. They have slightly different effects on the spectrum. They're not radically different from each other, so it almost boils down to personal taste. I would keep it in Gaussian unless you're looking for some specific effect of the Lorentzian filter. You can shift your spectrum to the right, and I'm going to actually zoom in so you can actually see this better. I can move the spectrum left or right by changing the B0 shift. And this is achieved by applying a linear phase to the free induction decay. So this is good, for example, if your NAA is not properly aligned, say at 2.01. So you can just very, very slightly shift it here until it's properly aligned. In this case, the spectrum looks like it's very well aligned, so the shift really doesn't make much of a difference. There is a lock B0 here, which doesn't have any effect on the data we have now, but in case you have multi-voxel data, this applies the same shift to all voxels. If you keep this off, you can shift each voxel individually. The area multiplier simply multiplies the magnitude of your data by some number. So you would really leave this at 1 at almost all times, unless you're trying to get your data to scale to some number that you're familiar with. For example, if I integrate the NAA here, sorry, I'm going to zoom in with the left button and integrate with the right mouse button. You can see the area here, and it says 75, and maybe that doesn't make any sense to me, but maybe I'm used to thinking in some units in which this value is equal to 10. So I might change the area multipliers until this kind of roughly equals 10, and then I can go and integrate the creatine and see, oh, okay, this is 4.89, and this also makes sense in the units that I'm familiar with. But really, you should keep this at 1, unless you're trying to do something very specific, like I just explained. Phasing is accomplished by the phase 0 and phase 1 buttons, both in degrees, or by holding down the middle mouse button, usually the scroll wheel, and moving up-down for 0th order phasing, or left-right for 1st order phasing. You can also do automatic phasing with the button here, which usually gives you a good initial guess, but I find that for the best phasing, usually manual has to follow after automatic phasing. You can select the pivot for the 1st order phasing down here. This means that when you change the 1st order phase, this particular point in the spectrum will not be affected. So for example, currently the pivot is set at 2 ppm, which is the NAA singlet, and notice when I hold down the middle button and move it left and right for 1st order phasing, the phasing of the NAA singlet at 2 ppm doesn't change. I could select a different pivot, say the creatine at 3 ppm, in which case now when I do my phasing, the creatine peak remains unchanged. The button here, Lock Phase 01, acts similarly to Lock B0. When you have multivoxel data, this makes sure that your 0 and 1st order phasing is applied globally to all of the voxels. The button here, Set Phase 1 to 0, simply sets the phase 1 to 0. So, just a simple example. Now I've set it to 50, click this, and it's back to 0, and it's actually kept at 0. So this makes sure, for example, when you move your mouse, that you can't apply by mistake any 1st order phasing. The DC offset button here simply lets you correct for DC offset, and it shifts the entire spectrum by a constant amount either up or down. The final buttons here allow you to left shift your FID, meaning remove a certain number of points from the initial time decay of the signal. So looking at the FID itself, this would simply remove, say, the first 1, 2, 10, 20 points. This is useful if, for example, due to some receiver artifact, these points have been corrupted. This is sometimes the case with maybe older scanners or older hardware. There are two problems with left shifting an FID. The first of which is that this introduces a 1st order phase shift. The second problem is that the first points usually contain most of the signal of your spectrum, so you usually take a pretty big hit to signal to noise if you remove too many points. I'm going to remove this back. The correct phase 1 here is supposed to take care of the 1st order phase introduced by the left shift at the moment it's not operational yet. This is version 0.7.3 of VESPA. Right, this concludes our tour of the Spectral tab. We'll have 2 more videos about eddy current correction and signal filtering, and then we'll move on to fitting.